Hello everyone, my name is Trayambak, and today I'll be talking about the NIM for Desktop Linux initiative. Without further ado, let us begin. Firstly, let's answer the question, why? So, to basically simplify things, NIM's ecosystem for Wayland and the modern Linux ecosystem has been lackluster at best. NIM on the X11 side has pretty decent support actually, with XCB and other packages that provide bindings for XCB, but the same cannot be said for Wayland, at least not before what we'll be discussing at least. For writing Wayland clients in NIM, or at least apps that work natively on Wayland, the only viable option thus far has been to use a C or C++ framework that handle talking to the compositor. This includes things like Qt, GTK, and sometimes even Enlightenment. This obviously comes with its own set of problems, namely that these frameworks are massive and pulling them in for minimal and light apps doesn't really make sense. So another solution to this was using something like GLFW or SDN. These libraries have full Wayland support as of their recent versions, but again, these libraries are written in C. They were never meant to be used like idiomatic NIM libraries, and as a result, they feel pretty clunky when you use them. Aggressive amounts of wrapping and abstraction could probably fix this, but there's probably a better path. So, now, how does one write a decent Wayland ecosystem in NIM? At its heart, Wayland is essentially a wire protocol. So essentially, the life cycle of a Wayland client is finding the socket where the Wayland compositor is currently running. You can actually get this via the Wayland display environment variable. So essentially, the client just goes up to the server, it connects to its socket, and it just starts talking to it with the wire protocol. So an important distinction over here, the client is not to be configured with a window. A client can own multiple windows. Those are XDG top levels or surfaces. A client can also own multiple surfaces, and surfaces are not equivalent to windows. Uh, so yeah, I just wanted to clarify with that. So on X11, you basically have the display server and optionally a compositor. On Wayland, you only have the compositor, and the compositor also does the job of the X11 server, i.e. the display server. So essentially, the compositor does a lot of the work that X11 previously did. This obviously eliminates a lot of the latency, but it also makes things a lot more complex. So, the first objective to writing a Wayland compatible windowing library is to get access to libwayland in NIM. To be more specific, I mean libwayland client here. So obviously the library is split into the client portion and the server portion. The server portion is a whole nother beast in of itself, and we'll not be talking about it today. Nayland. So, Nayland is essentially a project that provides high-level destructor integrated wrappers for low-level C-lib Wayland primitives, as well as different Wayland protocols client-side code. So as for the destructors, I mean awk, obviously. So it knows how to deal with awk, and it obviously integrates the low-level C destruction functions with awk. Its code job is to essentially just take libwayland client, take its CSMs, and to wrap them and abstract them until they feel more NIM-ish or NIMic. For context, this is some code that connects to the display. It initializes the protocol registry. It does a round trip with the compositor to populate that registry, and then it tries to access the WL compositor global interface. If we were to try this in C, it would probably be more like 30-ish lines or maybe even more with all the callbacks and stuff. But over here, it's barely like 7 lines. So you can see that obviously Nayland makes things a lot more simpler. So thus far, Wayland provides high-level wrappers for the following protocols. There's the co-Wayland protocol. This is required to talk to the compositor. There's XDG shell that is required to create desktop windows. There's fractional scaling that helps your app maintain sharp rendering on different outputs. This is important if you have different outputs with different scales so that your app does not look blurry or weird on different outputs. There's XTG decoration. This essentially just helps your client talk to the compositor and say, hey, I want client side window decoration. I'll be handling it myself. Or you can just pass compositor, hey, I want the server, that is the compositor, to handle window decoration for me. Then there's the system bell for foreground sounds. There's idle inhibit. This is a nice protocol. Let's just say you built a video player with Nayland. You'd probably not want the user session to go idle while they're watching a movie or something like that. That'd be pretty bad UX. So idle inhibit essentially just lets you tell the compositor, I'm inhibiting idle. As long as my surface is focused, you should not try to make the session go to sleep. Then there's layer shell. Layer shell essentially just lets you create desktop widgets like status bars, application launchers, and a lot more. There's cursor shaping. This is the same protocol that Chromium uses on Wayland. This essentially just lets you change the cursor's icon, like setting it to a spinner or the default state or the pointer or something like the resizing texture. Then there's the tablet protocol. This is mostly for interacting with things like Wacom tablets. It's a pretty specialized protocol. It's mostly used by graphics design apps, as far as I know there. Then there's presentation time. Presentation time essentially just helps your app ensure that the audio, if your app is showing a video, the audio does not desynchronize from the video that's playing in front. This can happen due to stuttering and other like unpredictable or non-deterministic factors. So it just helps your video stay in sync. Then there's content type hints. These are more of a suggestion. There's no standardized behavior across every compositor, but it essentially just lets your app tell the compositor, hey, I'm a picture viewer. Do not try to aggressively redraw me. Or you can say, hey, I'm a game. Try to minimize latency. This essentially just lets you save battery life or maximize performance depending on what your app does and what its needs are. Then there's tiering control. Tiering control essentially, firstly, I'm going to start off with the fact that Wayland essentially has the philosophy of every frame must be perfect. This is nice. This makes Wayland pretty smooth, but it comes with the downside that there's slightly higher latency. I wouldn't say a lot, but there definitely is a little bit more latency. There's no tiering, but the latency is slightly higher than having tiering. So this essentially lets you tell the compositor that you do not want vsync, you're okay with tiering at the cost of lower latency. Then there's Linux DMA buff. This essentially just lets you handle VRAM buffers directly, and it also helps you write something like a hardware accelerated screen capture tool. Then there's K1 blur. This is a K1 or KDE specific protocol. This is just used for blurring surfaces. So wrapping all of these would not have been possible without WrapGen. Uh, so WrapGen is a tool written in Nim that passes protocol XML files and generates client-side protocol wrappers that are fully integrated with awk when required. For context, all Wayland protocol files, including the core protocol, come in XML descriptions. So what WrapGen essentially does is it passes the XML and then it generates Nim wrappers for it. What these wrappers essentially do is just they take the low-level C libVayland bindings that BindGen generates. It's another tool, but it's much smaller and much simpler. And then it just generates awk integrated wrappers around it that are much nicer to use. It's not fully automated, but it's like roughly 95% of the way there, perhaps even more. The only part that requires human intervention when generating wrappers with WrapGen is resolving the imports for different objects, but that's about it. It's some 680 to 700 lines of code, but it's generated somewhere around 8,000 lines of code for Nayland. Without it would have probably taken weeks to write all of that, if not more. But there's obviously, Nayland is not perfect. A Wayland client library isn't enough to write programs for Wayland intuitively. There's a lot of like luxuries or even conveniences that libraries like GLFW or SGL provide you that Neelan just doesn't handle on its own. Uh, some of these are like, for example, if you want to do perform software rendering, you'll have to allocate memory buffers with memft and then share them with the compositor over the Wayland protocol. This is simple enough on the surface, but as you are factoring more things like resizing the window and all that, it becomes a massive pain. Then there's initializing an OpenGL context. So Neelan won't do this for you. So you'll have to do it yourselves. Then there's also handling input events in a standardized way. So that's basically some of the problems that come with it. So that's where Surfer comes in. Surfer is a high level, minimal, yet highly opinionated windowing library written in NIM. Wayland here is a first class citizen. For now, it's the only backend. Surfer's primary design goals are 1. Do one thing and do it decently, that being windowing on Wayland. So Surfer does nothing besides windowing and windowing adjacent tasks. Then there's the second design goal. Do not own the program's event loop and do not make any assumptions about it either. So this is, I'll explain this later on. Here's a basic app that uses Surfer. It uses OpenGL and it essentially just clears the screen and just draws a colorful gradient over it. It's not a gradient, it's more like colors that are just transitioning from one state to another. But you get my point. So, what can I do so far? First off, there's CPU rendering support. You can plug in Pixie, Cairo, or any CPU renderer into it. You'll essentially just have to copy the data from your Pixie or Cairo buffers into the CPU renderer's buffer. There's keyboard events. Surfer also maintains an internal timer. When Surf initially starts up, it just asks the compositor the repeat rate for your keyboard so that your program behaves identically to any other well-written client, at least when it comes to repeat rates. Surfer also handles OpenGL ES rendering. Surfer initializes and hands you over a fully initialized GLAS context, as one would expect from something like, let's say, GLFW or SDN. Then there's also client-side decoration and server-side decoration support. There's cursor shaping support. There's also tiering control support. And most importantly, there's layer shell support. I'll elaborate on this more now. You might notice that most of these things are actually wrappers around the Wayland protocols that we discussed earlier, and that is shell. Now, we'll be talking about creating desktop widgets with Surfer. Surfer utilizes the WL layer shell protocol to create desktop widgets on both desktop environments like KDE Plasma as well as compositors like Sway, Hyperland, Neri, and more. This protocol was initially created by the WL Roots team, but nowadays a lot of different compositors and environments support it. So here's a basic widget that essentially just occupies your entire screen on the topmost layer, and it uses the software renderer, but you can obviously use the GL renderer as well. Then it just fills out this text that you see on the second terminal window, and that's it. So it makes creating these widgets pretty like trivial, to say the least. Now we'll be talking about YBus. This is a bit of a departure from the things we've been talking about since they were mostly related to graphics and Valent. So YBus is a pure NIM dbus client. It's it's basically an implementation of the dbus wire protocol, and it also provides helpers for SASL authentication. That is the protocol that dbus uses generally for connecting and authenticating clients. Then it also provides you with a synchronous Unix sockets-based client. It also features a tool called BindGen to generate NIM bindings via interface introspection. It also implements dbus variant passing, as one would expect. The core of YBus, that is, the wire protocol parser and emitter, is written in pure NIM. This makes it pretty testable, I'd say. all the side effects are essentially just isolated from it via the client layers. So you can just create more clients, plug them into the client layers, and isolate all of the side effects over there, while the core remains side effect free. So here's a basic example. I'll just walk you through it. So firstly, we're creating a dbus client. We're then connecting to the user's bus. Then we can get then dbus, essentially the broker allots us a unique name on the bus. Then we can call a method over here. We're calling up, we're essentially just getting a property from system D's dbus interface. We're just going up to system D and asking it, hey, can you give us the version that system D is currently on? So system D just gets that request via the broker, and then it returns with a response. We can then unpack the response. It comes in as a variant. We can unpack it and then just print it out as a string. So if you look at the output over here, you can see that the serial is 1, obviously because we've only sent one message thus far, that being the authentication message. The synchronous client automatically sends that for you. Uh, that is the hello packet. Then we get to see our unique theme that was allocated to us on the bus. And then we get to see the system D version that our system is currently running. So, bindgen. This is not to be confused with Nayland's bindgen. I know I'm not particularly very creative when naming things. So, bindgen for Vibus is a tool that is used to generate high-level NIM bindings for dbus APIs. Its core feature is that it can use service introspection. So that's basically a built-in feature of dbus that allows services to support the introspection API. So tools can just go in, ask for the protocol XML directly from the services, and if the service supports it, it'll return a protocol XML directly. So for example, if you look at the code snippet, you can see that we're using pretty good looking NIM that looks nativish. But in reality, it's all behind a wrapper. So if you look at the output over here, you can see we're firstly checking for the server's information. So we get a list that says Marco. That's my notification daemon. Then it also returns the author's name and the version of the daemon. The second request that we're making is we're asking for the daemon's capabilities. So as you can see, it returns all the capabilities in a sequence as well. The body, it supports markup in bodies, actions, static icons, then some other stuff. Then we're making a notification request. So we're just saying hello Vibus. So if you just look down, you can see that Marco actually does show the request, the notification at least. You can look down and see that the text is identical. So it did in fact work, and all of the bindings for this were generated via bindgen. Another good thing about bindgen is that it's also type safe. I do have to warn you though, Vibus is still a relatively immature project when compared to something like Nayland or Surfer. It works, but it still has a lot of rough edges, it has a lot of deadlocking, and it has a lot of, let's just say, kinks that need to be ironed out. I'm welcoming all contributions to it. Now, the question naturally arises, are these actually usable? Well, they actually are. NITI is a GPU-accelerated terminal emulator written in NIM. It uses libvterm for handling the VT seat and Surfer for windowing. It started off as a CPU-rendered terminal using Pixie, but it eventually outgrew that because software rendering is way too slow without specialized optimizations. Nowadays, it uses NanoVG with GLES for all rendering. It can be configured via terminal. It runs basically every terminal program just fine and is fast. In fact, all of the slides that you've been seeing thus far, all of the code snippets that you saw in NIM are actually inside NeoVim that is rendered by NITI. Surfer and Nayland actually started off as the windowing layer for NITI. They were ripped out of the source tree and placed into separate packages. NITI's need to read from pseudo-terminal file descriptors is partially what led to server's design of not owning the event loop. As you might guess, that would be pretty bad. Nowadays, NITI also uses Vibus for its notifications API. It also uses Surfer's layer shell interface to allow users to embed it as a desktop widget. For instance, you can use it to run C-Matrix as your wallpaper. It sounds pretty stupid, but it works. So, for example, if you don't mind the background for a second, you just look at the layer config. You can see that we're configuring the layer to be in the background. Then we're configuring the anchors to left, right, top, and bottom. This essentially just tells the compositor that it's centered. Then we tell the compositor to set the size to 0, 0. This essentially is a hint to the compositor that tells it, hey, just expand the surface everywhere that to the entire output's worth. Then we're setting keyboard interactivity to none. You could set it to on demand or exclusive, and you'd get to use a terminal as a layer shell widget. It's not very, let's just say, practical, but nothing's stopping you really. So that concludes this presentation. I'd like to thank you all for listening to it. I would love to talk about more stuff that I've been working on for the past few months, but I'm afraid it would be a little bit too off topic for the general presentation. With Surfer and Nayland, I hope we can attract more programmers to write NIM. Partially because if you look at any of the cool Wayland related tools that have been coming up recently, like status bars, app launchers, and more, they're mostly written in C, C++, or Rust. Hopefully, by providing these libraries, we can attract more programmers to write NIM since it's really a joy to write. And maybe one day we can present a viable alternative to Rust or C++ to them.